So we've covered circular motion in our two-dimensional motion unit here, and we're going to spend more time on the next phase, which is projectile motion, also two-dimensional motion. Projectiles are very common in our everyday experience, so this warrants our attention and time. Now I will make the disclaimer here that this slide in particular, it's interactive with some demos, and so if I haven't already done them for you, you will want to ask me to do them. And I need to probably figure out how to add videos into my videos here. So that's something I gotta figure out, and so you can see what's going on as I describe it. But that's okay, because the main points are what I'm going to emphasize here. So what I can show you is if you take a book and a flat piece of paper and raise them up in the air and drop them, race them, and you observe what happens, say in the classroom where I'll do this, you should observe that the book wins. In other words, it hits the floor first. If you wad up a piece of paper into a tight ball and do the race again, I bet you can guess what you would observe. Yes, it's a tie, or at least very close. If we're talking just the height of the ceiling, then it's essentially a tie. Racing a book with leach paper, well, I'll just have to show you that, or I'll just have to keep you guessing. It's a tie there as well. So the conclusion from these quick observations is that objects accelerate at the same rate, but they require the absence of, you guessed it, air friction. Friction from air. All right, so the important thing here, we're getting rid of air friction and recognizing that gravity accelerates objects at the same rate. I want to show you why and give you a dynamic description of that, namely forces. So we know that A is sum of F over M. Well, what is the sum of the forces acting on the book, or any object for that matter? And again, we're not worried about air friction at this point. Let's eliminate it. Then the sum of the forces, there is only one, and it's gravity. So it's gravitational force over mass. Let's go ahead now and define the force due to gravity, which is mg. And what you're seeing emerge here is the reason why heavy objects and light objects accelerate at the same rate. The masses divide out, and the acceleration is just the acceleration of gravity, g. And intuitively, you can think of that as being because, well, a bigger mass has a larger force. The mg is bigger, but it's also more inertia, which is m, essentially. So the proportionately greater force is precisely canceled, if you will, by the proportionately greater inertia, both being tied to the mass. So the masses divide out. It's g independent of the mass. All right. Assumption being made is that there's what? No air friction. All right. So that's the first observation. That's good. And then we also have some additional observations that we can make. If I throw a ball up into the air while walking, I mean, if I'm just standing there tossing a ball up and down, so I'll try and do this here. Boink, 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 boink. See my cursor? Little red laser beam there. Up and down, up and down. It comes back to my hand. Now, if I'm walking, poop, 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 like this. All right, from your point of view, sitting there on your desk looking, you'll see the ball making, it looks to you like it's a different path the ball is taking. But that's a discussion of relative motion. We've already covered that. The point is I'm walking with it, so from my perspective it's just going straight up and down again. It returns to my hand, whether I'm walking or not walking. Now I've got a horizontal and vertical marble cannon. And I will demonstrate for you that when we shoot it horizontally and drop it vertically simultaneously, you will hear one sound as it hits the floor, indicating that both of them landed at the same time, so it took the same time to hit the ground. All right, that's important. Which means, by implication that there's something that can be said about the relationship between the vertical part of the motion and the horizontal parts. You know what that is? Well, then there's a projectile cart. So as a cart's moving along and it launches something up into the air, the question is, will it catch it again? And it will catch it again, which bolsters the previous conclusion, that partial conclusion we were coming to here. The ball's caught by the cart. Conclusion being that the horizontal and vertical motions are independent of each other. So that's the key point. We can analyze the horizontal motion, not worrying about the vertical. We can analyze the vertical motion, not worrying about the horizontal. And since they can be done independently, each one by themselves is easy to do. We don't need a complex parabolic equation to analyze projectile motion, which turns out to be parabolic motion. So that's where we're going with this. And those assumptions are key features that make this relatively simple. You're basically going to use the equations you've already learned for kinematics, and that's it. So we're going to enter into that. So I'm now going to describe and summarize for you all the equations of motion that we're going to need. And there'll be more here than you actually need, but I want to give you a relatively complete picture. Some assumptions being made based on the observations we just underwent is that the acceleration in the x direction, because the ball was caught back in my hand, because the cannon caught the ball after it was launched vertically, after moving, demonstrates that the acceleration in the x direction is 0. That's, again, not being concerned with error friction. That's another variable that complexifies our picture, and we can ignore it for our basic discussion of how the physics works here with motion. Acceleration in the y direction, negative g. And what I mean by that is the value of the acceleration is g. We know it's 9.8 meters per second. And yet it's in the downward direction, so I'm going to call that negative. So it's negative 9.8 at the surface of the Earth. So that's how that looks. So I have this table listed here, all the equations, 1, 2, 3, 4, 5, 6. We've already learned the 6 equations. I'm going to repeat them here quickly. Displacement is delta x, x minus x0. V average is displacement over time. Acceleration is delta v over t. Average velocity is the initial plus final divided by 2. 1/2 v0 plus v. Remember, that's a derived equation, not a fundamental. These were fundamental. This is derived, as is number 5 and 6. Displacement is initial times time plus 1/2 at squared. V squared is equal to v0 squared plus 2a displacement, or delta x. But now, because we're doing two-dimensional motion, parabolic motion, projectile motion, we're going to split this up into the vertical and horizontal components because of the independent nature of those two motions. We can do that. So for vertical, we have y instead of x. That's the basic difference. So we have y minus y0. y0 is our initial position, usually 0, unless otherwise stated. Delta x for horizontal is x minus x0. You're going to notice that the information I put in the horizontal column is going to be redundant and fairly trivial, which I'll summarize right at the end. So Vy average, delta y over t, change in y over t. Well, okay, it's true, but not that important for the most part for our problem solving. X is equal to Vxt. Vx is constant, so the x position is motion times time. That's actually a useful equation for the x direction. Now Vy, equation 3, Vy0 minus gt. It comes directly from here. We've seen that before. I'm subscripting y because we're only worried about the vertical in this column. This is a really good and useful equation. Now Vx is equal to Vx0 is the corresponding horizontal part. In other words, the velocity in the x direction is what it started out being, just a recognition that there's no acceleration vertically. Vy average, 1/2 Vy0 plus Vy. Same thing we had from the basic equation. And over here, Vx is equal to Vx0. Same thing again. Just doesn't change. So you don't have another equation for it. Equation 5, y is equal to Vy0 minus 1/2 gt squared. But that's really displacement in the y. Assuming y0 is 0, then you'd have y is equal to y0 plus Vy0t and then minus 1/2 gt squared. Or you could just put delta y here, which is y minus y0. Note that there's a difference. The plus went to minus. Why? Because my acceleration is negative g. That's why I put that minus sign there. All right. X equals Vx0t. There is no acceleration, so this term doesn't even have a counterpart over here for the horizontal direction. And finally, Vy squared is Vy0 squared minus 2g. The plus went to minus for the same reason before. Acceleration is g. Y. Again, if y0 equals 0. Otherwise, consider this delta y. Vx squared is Vx0 squared. Nothing new there. So, I will encourage you, if you're following along with your notes, you might want to circle this one, equation 3, equation 5, equation 6. Those are the really useful ones. What's really useful over here? This, x is Vx times t. I'm assuming you know this already. So this for projectile motion, and understanding that this is true. Vx is Vx0, which is also Vx final and Vx intermediate. It doesn't change. So now in the next video, we're going to start to analyze a few situations where we're utilizing these motion equations to solve projectile motion problems. See you in the next video.